Welcome back. So this is video 2 of the transition metals. So this video is intended for Thursday. Thursday, what? 19th, isn't it? Yes, 19th September. You can watch it in advance, of course, as I actually tried to do before, but didn't quite make it. So we're going to look at 28.2, and again, there's a lot of stuff here. It's a little bit repetitive, but, well, let's plow our way through. So describe and explain the reactions of transition elements. Actually, this is very bad. It's not the elements that we're going to be using. It's their aqueous ions. That's what I'm going to assume this to mean, because there's no point in just taking an element like copper and reacting with a ligand, because it wouldn't really work. You need the ion. Remember, ligands are based with, they make coordinate bonds or dative covalent bonds to transition metal ions. So because we have this ligand, it is referring to the reaction with metal ions, not elements. So they don't have very good wording here. So I'm going to assume that it means the aqua ion. Most of these ions of the transition elements are considered inside of an aqueous solution. Okay, so we're going to take the transition element ions, the aqua ion, and we're going to make some complexes using different ligands. So we're going to do like a nucleophilic exchange, like I mentioned in the previous video. And in particular, we're going to look at copper 2+. See, so it can't be an element, is it? Because it's got an oxidation state of 2. Elements have an oxidation state of 0, so their wording is not very good here. I know what it means. Transition elements is the elements found in that series, but well, they could have worded it a little bit better. And also cobalt 2 ions will also be considered. Okay, and the ligands that we're going to use, these are very common A-level-y kind of ligands, is water. That's usually what we start with. Ammonia, hydroxide ions, and chloride ions. So we're going to look at different reactions of those. And they will come up later in when we do something called K-stab. It's an equilibrium constant. It will have to do with these ligands. And also the colors of these compounds. We can generate a lot of colors using these ligands with these metal ions and so forth. Okay, then we're going to define the term ligand as a species that contain a lone pair of electrons. That's not strictly speaking true. That's just an A-level context. It could be a pi bond as well. So for A-level, we will just use this definition. But it's not a good definition. It's a bit limiting. I suppose as an introduction, it's not too bad. But anyway, so it has a lone pair of electrons which forms a dative covalent bond to the central metal atom or ion. I'm not so sure about this atom thing. I don't know why they put it there. It should really be ion. Ligands don't really react with metals per se. So again, I think they could have improved this quite a bit actually. So I would kind of be tempted to scrub that one out. And I would say reactions of the aqua ions, as I mentioned earlier, that'd be even better than before. Aqua ions of the transition elements. So anyway, okay, so we already discussed ligands a little bit in the last class, so we should have a little bit of idea as to what that was. Remember, inorganic, we would call that a nucleophile. That's the organic equivalent. Okay, and then we need to understand these terms monodentate. Okay, and that covers these various ligands. A new ligand here, a cyanide ion, is also a ligand. It's also a nucleophile, of course. Bidentate ligands. So we've got monodentate and bidentate ligands, and these are a little bit more sophisticated molecules. It's a bit longer, but no problem. We'll deal with them. And polydentate. So we've got monodentate, bidentate, and polydentate. So mono obviously means one, bi means two, poly means many. We have this EDTA4-. That's an acronym. It means ethyl-diamine tetraacetate. It's a bit long, so we'll stick with the acronym. So we'll look at that as well. Define the term complex as a molecule or ion formed by a central metal atom. Again, not quite sure about that. That doesn't really come up. Surrounded by one or two more ligands. Now, the chief examiner for paper 4, he mentioned that he didn't actually like the Cambridge wording of it. And he was a chief examiner. Because if you have Na plus ions in aqueous solution, those ions, of course, are surrounded by water molecules. We get ion-dipole interaction. But that would not be a complex. So we can make an aqueous solution, but it's not a complex even though it's surrounded. So this definition here, surrounded, is actually poor. It's a bad way to describe it. It should say covalently bonded to one or more ligands, right? Or coordinatively, if there's such a word, bonded to one or more ligands. So this surrounded by it's not good. So they've done a pretty lousy job of this chapter so far, I think. Anyway, so then we need to describe the geometry, the shape and bond angles of the transition element complexes. That's a bit better. To include linear shapes, square planar. We've not looked at any square planar shapes yet. Tetrahedral, yeah, we've seen them before, and octahedral, we've seen them before as well. So, after that, state what is meant by coordination number. It's quite easy. Predict the formula and the charge of a complex ion given its metal ion and charge or oxidation state. It's kind of like calculating oxidation number for the previous compounds that we did, like sulfate ions, chromium inside of dichromate ions, blah, blah, blah. So there's a bit of new stuff here. There's also a little bit of repetition and a little bit of old stuff. So let's get moving. Okay. Describe and explain the reactions of transition element Aqua complexes with these ligands. So let's consider them. So Aqua complex. Aqua means water. If you interested in these kind of things, you look at the food labeling. When you buy some food, you'll often see aqua mentioned as one of the first ingredients. And usually these ingredients are listed in amount order, so that the highest amount first. So if you see aqua in something, basically you're just buying some kind of flavored water. It's a clever way of disguising the word water. Aquaman. Okay. Aqua complexes. So these basically, they're all the same. You typically have a transition metal ion, and it's surrounded by 6 water molecules. We drew a picture of an iron version of this in the previous video, and it's got some kind of charge depending on what metal it is. I'll just put X plus. So you'll notice that we're using a square bracket. Square brackets are used to kind of show a complex when necessary. So a bit like concentration used a square bracket, we also use a square bracket here. I don't know why they didn't come up with a new fancy bracket. Maybe they could have done something like this, right? Whatever, but they didn't. So these square brackets here, they mean complex, not concentration of. They're just a way of encapsulating everything into one space, just like a normal bracket would, encapsulate kind of like some kind of, equation or something like that. Right, so if you got like 4 times that, it means 4 applied to everything, right? So we're using brackets in the same way as a mathematician would do, but we tend to use square ones because we tend to use the inner round braces, or what do you call them, parentheses. And we tend to use them for like the amounts of ligand present. So encapsulating all of that stuff is the square bracket. Okay, so it means complex. Okay, so we always have 6 of these, no matter what metal it is. So we always have 6 water ligands. covalently bonded to, or surrounded by, as it said in the syllabus. Let's say datively bonded, it's easier to spell. Having said that, I can't spell it. Datively bonded to metal ion. So the great thing about aqua complexes is they're pretty much always the same. We have 6 water ligands datively bonded to the metal ion. So we mentioned the aqua one of iron, so we have that. So we could write it like this: FeH2O6, and the charge on that was 2 plus ion in the very beginning. So we would write our complex ion like this. I also did the copper with chloride ion. So if you remember, it was a tetrahedral shape. We'll get on to shapes later. And there was a charge on this thing. It was a 2 minus charge. Okay, so if you wanted to word that, you could put the square brackets in here, but they're not really needed because, well, the ligand only has like one symbol. It's not like H2O kind of style. So you could put a square bracket in if you want, but it's normally ignored. It's normally just written as Cu Cl4 2 minus. All right. Okay, so with the water ligands, there's always 6. Other ligands, you often have different values. So for non-aqua ligands, you can get other numbers. So there's a little bit of variation with the non-aqua ligands, but the aqua ones themselves will always have 6. That's a good reference point. That should be the base level of thinking that you have when you talk about complexes. Okay, so if we take some, let's use the aqua copper, H2O6, of course. And the charge on this is 2 plus. So the charge actually is kind of determined by the charge on the ligand and the charge on the metal that we started with. Water is a neutral ligand. There's no overall charge on it. So this plus 2 obviously must be the charge on the copper. And also it can be used to give us the oxidation state. Okay, so anyway, we have this complex. It's a 2 plus charge complex, and you need to know the colors of these things. This is blue. It's a blue. You'll see a blue solution because it's an aqua complex. It's dissolved in water. Let's put the AQ symbol in. AQ. Okay, so we have a blue solution, and if we throw in some hydroxide ions, for example, we'll do some of these experiments in the lab. If I throw in some aqua hydroxide, then what can happen is a reaction between these things can take place, and over a period of time we can get this forming, which is now a solid. And the color of this is also blue, typically pale blue, maybe sky blue is the word used to describe it. Pale blue. Cambridge always say, oh, be careful about how you name the colors. Don't really have fancy color names. And I can semi-understand why, because some people may not quite understand that fancy name, like an evil red color. You know, what is that? You know, other people might have a different vision of it in their head or whatever. But pale is an accepted color, and blue. So always just try to have a simple color. And if you need to qualify it with a bit more description, pale or dark, those kind of things are acceptable. Now it's a solid. It's a sparingly soluble compound, so we can start to do some KSP stuff on this. And because Cambridge specifically mentioned copper in here, then don't be surprised if this is an example of something that will come up in your exams for KSP. Okay, so what have we done? Well, it looks like we've changed the ligand, right? We've changed the water ligand for hydroxide ligand. But you have to be very careful with this. That's not actually the case. We'll discuss that in a bit more detail later, okay? For now, I just want to go through the reactions of these things. Okay, so hydroxide ions in the presence of aqua, Cu2 plus. Remember the shorthand for that was simply Cu2 plus aqueous plus 2OH minus. This is how we would write the equation previously. Oops, that should be AQ, not AG. That's not very good, AQ. We would write that like this. COOH twice solid plus, well, we should really, if we want to do a balanced equation, we should write that also. So that's how in the past we would write it. We'll look at this reaction, like I said, in a bit more detail later, but we know that hydroxides will be formed because the solubility rules tell us. So solubility rules, they will assist us, but you can actually use something else to predict whether it will be a solid. It can help predict the state of the product. Now there's a nice alternative way to predict that it was a solid, and that is looking at the charge. Okay, so the Aqua complex, the Cu2 plus Aqua complex is charged. Therefore, it's going to be soluble. The kind of interaction that we have with water solvent will be an ion, or complex ion, I should say. Let's just write this first. Ion dipole, i.e. complex ion dipole, interaction. And they're stronger than hydrogen bond interactions. So ion dipoles, yeah, they're soluble. Very soluble. Okay, so the initial reactant was charged. And the product, what was that? CuOH twice. That's not charged. And when you have a transition element complex which is not charged, then pretty much all the time it's not going to be soluble. It doesn't have that ion dipole interaction anymore. So there's no more ion dipole interaction, or bonding, or forces, IMFs, whatever you want to call it, dipole bonding. So therefore it will precipitate out. A precipitate will form. So the solubility rules tell you that all hydroxides are insoluble with the minor exceptions of group 1. And what else? The barium, the kind of the latter group 2 ones. Everything else with a hydroxide will be insoluble. So here we have another way of doing it. We can just look at the change in the charge. It went from charged into non-charged, therefore not soluble. Precipitate will form. So this means that any aqua complex that you choose, let's do the iron one yet again. I have no idea why I'm picking iron all the time these days, but I am. So if I took that aqua complex and I threw in some sodium hydroxide solution, and I know that I'll get some hydroxide precipitate forming, and those water molecules, those water ligands, just kind of depart. So if you want to have a balanced equation, you can just show them separately. So again, the point is we have a transition metal compound, which is hydroxide, and it's not soluble anymore. Precipitate will be seen. And they have colors. This one is a kind of a green gel-like precipitate. Green gel-like precipitate. You don't have to say gel-like, but it sometimes helps you visualize what it would look like a bit more. Again, we will do this in the lab. You've seen this kind of stuff already, but you probably forgot it. It's been a while now. Okay, so any metal complex, we can do nickel aqua complex, which again will always have 6 ligands. This one is +2 charged as well. Nickel +2 is probably the most common oxidation state of nickel. And we can throw in yet more NaOH. Good day for NaOH sellers. We will end up with a non-charged species, which I know is going to be precipitate. And 6H2O. H2O liquid. So this nickel one is a kind of, I think it's a green color, isn't it? It's a green solution. It's dissolved. So it's transparent. You can see through it. It's just a green see-through liquid. And nickel hydroxide, oh crikey, what color is that? That's, I've forgotten. Is it a green solid? I'll have to check that one actually, but okay. The point is, once again, a precipitate had formed. So any aqua complex will do this. All aqua complexes will form uncharged what do you call it? Precipitates, PPTS. Now some of them are amphoteric, and they will actually react even further. We saw this when we did aluminium chemistry a little bit. So let's just have a kind of little star here. Some are amphoteric. Hydroxide precipitates, which means that if you add more OH minus, then the hydroxide precipitate will react further with hydroxide, and then we'll get a negatively charged complex, and therefore it will dissolve again. So if more NaOH minus is added, a further reaction takes place. So chromium is an example of this. For example, if you got chromium 3 plus aqua. I'm just going to use the short form at the moment. We can add some NaOH, it's actually a reactant. Aqueous. I'm not going to bother about the balanced chemical equations at the moment. I don't care how many NaOHs is needed, but we can make this. I think this is also a green solid. I know it's a solid because it's not charged anymore. And my solubility rules tell me. But if I take some more NaOH, then I can actually make a CR. Well, I can make OH4 minus first, and then we might even be able to go all the way to CrOH6. So I'm just going to do this one step further down the road. So now it's ionic again. Therefore, this complex ion will be soluble. So we will see the precipitate dissolving as this compound forms. Okay, so you can use that as a good way to kind of figure out whether you have an amphoteric hydroxide or not. The non-amphoteric ones, manganese hydroxide, MnOH2, put a bracket there, is not amphoteric. Which is a kind of a beige color precipitate, beige, or sometimes sandy is used. Well, no, that's a bit dodgy because sand can have different colors, right? Most people think of it like as a pale yellowish, creamy yellow. Beige is a better word, I think. Sandy colored precipitate. It's not amphoteric, so if I add NaOH, nothing happens. Precipitate remains. So, all aqua complexes will give a precipitate with hydroxide ions, but some of them will react further depending on when they're amphoteric. So the ones that are amphoteric are the chromium hydroxide precipitate, zinc, which is not a transition element, but it is a D block, and it often is mentioned in this topic because it shares a lot of chemistry, but it doesn't share all of the chemistry of the transition elements. And aluminium, also amphoteric hydroxide precipitate. That's not even a D block element, but sometimes it raises its head if you have to distinguish, for example, the transition element amongst them. Then you would do various tests on these, and depending on their color and what happens. My charge is wrong. Sorry, my number here should be 3. Yeah, so depending on what happens when you add extra hydroxide and the colors that you get and so on, you can distinguish these ones. Okay, so all aqua complexes will react with hydroxide ions. So the key one is copper. Blue solution will give a blue precipitate. Copper is not amphoteric, so it will stay here. It does, however, do something if you just leave it lying around in the test tube. So copper hydroxide is not amphoteric. If you leave it over time, this pale blue precipitate it will tend to lose a molecule of water. So it tends to form CuO over a period of time. So if you leave this stuff in a test tube, like even for an hour or two, you can begin to see copper 2 oxide forming, which is a non-charged species, so it's going to be solid, and it's black. You'll see some black stuff beginning to appear in your test tube. Okay, so it does something else, but it's not an amphoteric kind of acidy base kind of reaction. Okay, so yeah, they all make hydroxide precipitates. Some of them will react further depending on whether it's amphoteric, and some might dehydrate further. You lose a water molecule from here. All right, so that's copper with hydroxide ions. Let's look at the other ones. Copper with ammonia. So we're sticking with copper for now, and then we'll talk about cobalt later on. So again, we're going to start off with the aqua complex plus NH3. Now this is there's a lot of stuff going on here. It's not so obvious when you see it in a test tube exactly what's happening. So what do we get in this reaction? Well, initially we get a precipitate forming, a pale blue or sky blue precipitate forming. You might say, oh, that's strange, because ammonia is neutral. If we had a neutral ligand to a copper 2+, then overall it should be a positively charged complex, and therefore it should be soluble. Well, yeah, I would agree with that, but that's not what's happening in the beginning. The ammonia solution contains hydroxide. So ammonia from the reaction of ammonia gas and H2O. Okay, most of it just dissolves. So we get NH3. Well, pretty much all of it will dissolve, to be honest with you. NH3 Aqua. And at this point, once you've dissolved it in water, well, ammonia is a base. It's a weak base. But it's strong enough to rip off a proton from a water molecule. And water, as you know, can be an acid or a base. So some NH3, not much. It's a weak base, remember? So the amount of ionization, the amount of reaction which causes the ionization will be quite small. So some NH3 reacts with H2O. So here's a little bit of the dissolved ammonia. There's a chemical reaction with H2O. Weak base, weak acid is going to give a salt, ammonium hydroxide. And of course these are charged species, so these will be floating around independently of each other. Unless you remove the water, then they will stick together. So have ammonium aqua ions and hydroxide aqua ions. So now you can maybe understand where that pale blue precipitate came from, because any solution of ammonia will contain hydroxide ions, and they are more active than the ammonia. There's an equilibrium kind of thing going on here. There's competing equilibria. At the beginning, hydroxide is the one that reacts with copper. So the copper 2+ itself is dissolved in water. It's the Aqua complex, right? Remember, I'm just using the shortcut, or else we'll be here all day. Reacts with the hydroxide that was formed in the ammonia. That's why ammonia is sometimes called ammonium hydroxide solution, because it contains these ions. So it's this OH- which will initially react with copper, and you get what you had before. You get copper hydroxide, solid. Okay, but if you add more ammonia to the copper solution, that means the concentration of ammonia in the mixture increases, because it dominates the percentage of the solution present. So for example, here's let's have a beaker. Here's a beaker of copper aqua. Okay, and then you're going to be pouring ammonia into this ammonia solution. So when this ammonia is first introduced to this liquid, the concentration of ammonia goes down because we've got excess water in the copper aqua. Okay, so it's not very concentrated. But if you keep on adding more ammonia, so adding even more, then this diluting water becomes less important, and the concentration of ammonia in the mixture begins to increase. And when that happens, then the ammonia, the concentration gets large enough for its equilibrium to dominate the system. And then the ammonia starts to make its presence felt. So, on addition of excess ammonia, and the easiest way to do this is to add concentrated ammonia, instead of having to keep on putting in drop a pipette's worth of ammonia again and again and again. Just get some conch ammonia and throw it in there straight away, so immediately the concentration is very high. But conch ammonia is quite horribly smelling, so we tend to minimize its use. So on addition of excess ammonia, then the NH3 concentration increases in the mixture. And so its equilibrium reaction begins to dominate, or I don't know a better word for dominate, but begins to override the copper and the hydroxide reaction. So essentially what we could write, the Aqua complex 2 plus NH3 solution, and if we wanted to, we could, oh, my cues keep on looking like cheese. We could, if you wanted to, write the intermediate copper hydroxide, or we could just cut to the chase and we could just write, oops, I need some space. We could write the product of that reaction, which weirdly enough is written like this. So some of the ammonia actually sticks onto the copper. Sorry, that's the wrong way around. CnH2O twice. I'll put the ammonia first actually, because it's the most important one. Doesn't really matter how we do it, but H2O twice. And it will have a charge because the copper was 2+ in the beginning, and these are neutral ligands. H2O is a neutral ligand. Ammonia is a neutral ligand. So the complex actually has a 2+ charge over its whole being. So now we've made a soluble ion again. Therefore it will obviously dissolve. The precipitate here will dissolve. So the precursor precipitate, the one that we had before, dissolves, and we end up with an amazingly colored, sometimes called a royal blue. That's royal blue solution. It's very intense, deep blue. That word deep blue is often used to describe it. It's a solution again, the precipitate dissolves. So you can sometimes show the intermediate compound when you do this, or you can just go from the very beginning. But if you do this drop by drop, adding the ammonia, you will notice the pale blue precipitate, which eventually will redissolve again to give this deep blue solution. Sometimes this is left out. Depends on how much detail you want to give in an answer. If the question's only looking for the product of the reaction in excess ammonia, then no need to talk about the middle bit, right? So we have a blue solution. We'll give an intermediate pale blue precipitate, which on addition of excess ammonia will give a royal blue solution. Now, this is asked about a lot, so you must be pretty hot on this, right? It's commonly asked for. maybe step by step, or maybe just the whole thing. But you must be aware of all of them and description of what happens. Even though you're not doing practicals anymore, practical exams, you are still often asked about this. And description or observations seen. So keep that in mind. Okay, so we've done copper with hydroxide, copper with ammonia, and the last one really is copper with chloride ions. Now this is this can be a source of trickiness. Okay, so well, we know that this is a blue solution. When we add chloride ions in the aqueous sense, some of these chloride ions will actually stick onto the copper. We can get the copper chloride complex that we mentioned before. There's no hydroxide interference going on here. But if the concentration of chloride is low, and we're doing this inside of an aqueous environment, you will typically see a green solution. But it's not really green. Because what's actually happening is the compound copper tetrachloride in the solid phase, i.e. pure, right? This is the point. When it's pure, it's actually a yellow color. But if you're using dilute chloride ions and it's all in an aqueous environment, so the green that you see, let's put that actually in green. It's actually a combination of the initial blue aqua complex and the real copper chloride. Is a color combination of the remaining reactant which is of course blue solution, and the copper chloride product. We don't get a lot of this. It's not like a 100% reaction. There's a bit of an equilibrium going on, which is yellow. So green plus, blue plus yellow is green. So this is what we actually see when we do it in these conditions. If we change the condition to using concentrated HCl, which of course contains loads and loads and loads of Cl minus ions, so if conc HCl is used and the water in the whole mixture is very low, then we will begin to see this yellow color dominate. It will go from a kind of greenish color and it will gradually kind of get more and more yellow as you add more conc HCl. Okay, because now the concentration of the aqua complex, so So this is quite small, which is blue, is small compared to this massive one now. CuCl4. You know, you can easily comprehend that the color of this one will begin to take over. So this little yellowy stuff is that. Okay. So you have to be a bit careful with the observations here. If it's dilute chloride ions, initially you will see green. If you keep on increasing the concentration of chloride ions, it'll start to go yellow. If it was a pure compound, if it was a solid, it would be yellow. But of course there will be counter ions there, right? Copper chloride is 2 minus charged ion. There must be a counter ion here to make it a neutral compound if you're talking about the solid. Okay, so let's just recap, right? So copper chloride, solid. I'm going to leave it like this. The point is that it's solid equals yellow. Dilute copper chloride complex, it looks a bit green. Okay, so please be careful with this. I think obviously Cambridge know about this problem, so they're actually a bit kind here. They tend not to get into the kind of the grey zone. But they have used this, what is the color of this compound question before in exams. And, well, students doing it in the lab, they just report what they saw, but they forget that I was in an aqua environment where the concentration of chloride ions was very low. Okay. So, what about the shapes of these things? Well, the copper hydroxide is linear. You could draw it like this. So there's a charge on this. Remember? Sorry, there's no charge on this. It's a solid. It's a linear structure. It's a bit like Ag. Yeah, a bit like Ag and H3 twice. The silver diamine complex. Remember, this is the active species for Tollens test. So word complex ion. It's a is it transition? Yeah, it's in the same group as copper. So it's a transition metal ion, Ag plus, with just got 2 ammonias bonded to it. The shape of the ammonia one that you get after this is a bit complex, maybe a bit hard to remember. We actually have a copper atom at the center of the complex, but we have 2 different kind of bond lengths, and those bond lengths depend on what ligand is attached. So we have a axial bond. So here's a water molecule. Let's just say OH2. No need to do the structure of that. And we have another long axial water molecule down here. And this is an octahedral complex. So we have this stuff kind of going to the back with the ammonias on it. And these bonds are a bit shorter. Maybe I should have deliberately made it look shorter. Let me just make it like this. So I'll have a little stubby bond here. NH3. And there's a stubby bond sticking out here. Again, it's short. This is coming out towards you. There's another one coming out towards you. And there's one at the back here. So this is a distorted octahedral shape. So the axial bonds are long. And the equatorial bonds are shorter. We have 4 equatorial bonds, just like we had in previous octahedral complexes when we did, remember? PCl5, that wasn't octahedral, but it had equatorial bonds. SF6, that was octahedral, and it did have equatorial bonds as well. So we see the equatorial positions and axial positions before. So this one just happens to have 4 equatorial. Oof. My God. This happens to have 4 equatorial bonds. And each of those positions on the equator is occupied by the N species. The axials are occupied by the H2O species. So it's a bit odd. So why is it distorted? Well, we kind of have a long kind of thing that goes like this. So if you were to draw kind of octahedral shape, it would look a bit like that, I think. Oops, that's not very good, is it? That's not much better either. Let me cheat a little bit. So it's kind of like an extended or stretched octahedral. This is obviously a massive exaggeration, but just to give you the point. So the equatorial region is in the center, and you can see it's elongated. So it's not a symmetrical octahedral whereby each of the lengths will be equal. Oh my God. So this would be a better example of a symmetrical one, even though I can't draw it. So the length of the side will be equal all the way around this structure. Here the length of that is much greater than the length of the equatorials. So we get this. So it's odd, right? But you're expected to know it. That's why it has that strange formula. Quite a long thing to draw, it gets a bit tedious after a while. And it is a charged species, the deep blue, royal blue species. Okay, what about the chloride example? Well, that was the tetrahedral, wasn't it? Did we do that just now? No, we didn't. Okay. I think I did it previously on the last video, but let's formally draw it. So it is actually tetrahedral, 109.5. The bond angles in here, you should know what they are, right? Of course, we have 90 degree in the equatorial, and we have 90 degree in the axial, but you must not forget there's another bond angle, whether it appears on mark schemes or not. It may appear on your mark scheme, and that's 180 degrees. We have this angle between 2 different bonds, so you should also include it. I know 290s is 180, but some examiners will perfectly rightly actually expect you to write that number. Okay, so this is a tetrahedral. Okay. So distorted octahedral, tetrahedral, and linear for the hydroxide. Okay, so what other reactions do we need to look at for this copper? Okay, so just the complexes, right? Okay, so let's do the cobalt now. Cobalt. It's quite a toxic element. I think cobalt is named after Cobalt, which is a kind of German word for goblin, I think. So they used to extract cobalt in mines, and it's a toxic element, and there's all these other toxic things present there as well. So cobalt is quite nasty stuff. So again, we're going to start with the Aqua complex. And as we know, all Aqua complexes have got 6 water ligands on them. The cobalt will make a 2+ ion. All of the transition elements will make a 2+ ion because they lose the 4s electrons. That's the highest energy. Remember we talked about this expansion of the 4s? And we have the 3D wrapped inside it now. Once we filled it, after filling. So the 4s, as a metal, will get lost. Metals don't like to hold electrons. So they will all make a 2+ ion. It's the most commonly seen version of these ions. All right, so what color is this? This is a kind of a pinky peach color. Pink color. And it's a charged species, and it's soluble. So we get a pink colored solution. The reaction with hydroxide, I'm going to use the shorthand now. It's a bit odd. You get multiple things appearing. So when you take ammonia, sorry, what am I talking about? Okay, we'll do the hydroxide. When you take the hydroxide and you add it to cobalt, initially you will see a blue precipitate. Of course, it's a solid. But over time, this kind of turns into a gray. And then over even more time, it goes to a kind of a peachy pink. So it is quite complex, and I don't think you're expected to know what these species are. There are multiple things which are happening here. So this is the observation, but you wouldn't be able to explain what these are. So you must say that you see these things forming, especially the initial blue precipitate. It's very obvious. What these are equals, oops, not expected to identify. But the final product, the peachy pink color solid precipitate, is cobalt hydroxide. If you have pure cobalt hydroxide, it will look peachy pink, and if it's very intense, it'll look maybe slightly orangey. Remember, the eye can see two things. It can see wavelength and intensity. So, okay, this bit, yeah, you must know that this is sometimes not required, the gray thing. It's just basically a transition of the blue color into the peachy pink. The blue dissipates, and the peach begins to take over. So that observation definitely, this thing here definitely, and this thing, of course, absolutely, definitely, the reaction conditions. So the grey bit can kind of be skipped down. But you will see this when you do the reaction. Okay, so it's a bit odd, the cobalt. Cobalt with ammonia. So again, I'll do the abbreviation form. A couple of things happen here. We get a direct, we get a precipitate forming for the same reason as we had before. The OH minus in here will give a hydroxide precipitate initially, and on excess NaOH, we end up with cobalt, which has got 6 ammonias on it, and that will be charged. So the precipitate that you see at the beginning will dissolve. And over time, this actually does what we call aerial oxidation. And this cobalt compound becomes NH3,6. It looks the same, but the charge goes to a 3+. So this is over time. And again, it's charged, so it will be soluble. I didn't write solid here. Okay, I think this color is a kind of it's an orangey, rusty kind of color. Orangey, kind of like orangey river, muddy kind of color. Sometimes you get orangey rivers, right, when it's been raining a lot. And this is a kind of a brownish color. Sometimes they're kind of interchanged. It's very difficult to describe the colors actually, because it's really dependent on the intensity and the concentration of these ions. It can look quite different, but they do have this kind of orangey brown thing in common. I'm going to try and bring up a image. So cobalt and ammonia to kind of hopefully show you this. Cobalt and ammonia. Oops, I didn't spell cobalt right. Okay, I've just got stylized drawings of it, not the actual real stuff. Okay, I'll take this image from Chem Guide. I'll paste it in here. Okay, so this is what they say. You have your pink cobalt hexa aqua at the beginning. The well, I think this orange color is actually inside of a pink liquid. That's an orange color. This green color is inside of a pink liquid. So to see the color of this, you actually have to pass through the pink liquid, which actually affects how it looks. This is it's the common problem when you're looking at a substance through a colored liquid. The substance itself actually, it's very hard to get the exact color. You'll have to remove all the pink liquid really to see this color. So it is complicated. Don't worry, we'll do this in the lab, and you'll get hands-on experience of knowing what it looks like. So we get the hydroxide precipitate in the beginning, which you can write in its long form if you wish, or you could just abbreviate it to the shorter form, which is nice because easier. Okay, and then we get total loss of all the water, so it goes that kind of browny orangey color. This is used. This is made by using human colors, so of course it's not going to look exactly real. It's a bit of interpretation going on here. And then finally, if you leave it in air a bit longer, you get oxidation. And the principal species there is the cobalt hexaamine complex with a 3+ charge. So, like I said, the intensity of these things makes them look very different depending on which experiment that you're doing. So, they'll probably not go and ask you about these colors simply because they're so variable. Okay, but you must be able to state the chemical equation, the stuff that's formed, whether it's soluble or not, And if you say orangey brown or something like that for either one of these, you can see that this complex is semi-orangey brown, this is semi-orangey brown, then you should be okay. It is a tricky reaction. Okay, right, we've only got the chloride left. So cobalt, aqua, 2+, and HCl. Again, we can use aqueous or conch. This will give a blue solution. And actually it's very temperature sensitive. So it's actually a very good way of demonstrating the principle of equilibrium. If you do it in a hot condition or a cold condition, this equilibrium, it is an equilibrium, it can be disturbed. And of course this is pink, so we get a nice color change. If the equilibrium moves to the right, then it takes on a blue appearance. If the equilibrium moves to the left, it takes on the pink appearance, and that can be adjusted very easily just by even small degrees of temperature. So it makes for a very good demonstration. Okay, so what do we get? Well, we get cobalt hexachloride, just like the copper. It's also 2- charged. You can put the square brackets in if you wish. Again, it's not normally done because we just have a simple ligand here. We don't need to overkill the brackets. But okay, so that's copper and cobalt. They are the essential species that you must have primarily at the front of your mind if you are asked about these reactions. Okay, what about the shapes of these things? We didn't mention the shape. Well, this is octahedral. And this is tetrahedral. And the hydroxide, just like copper, was linear. This kind of peachy pink. Okay, I'll leave that video here for today. We've done quite a lot. I don't want the video to be too long. It'll take ages to render and upload. So we will continue this chapter in video 3. So we haven't finished this particular part. Where is it? It's disappeared. So we've just really covered the first bit. But a lot of the stuff we've talked about actually is going to be relevant down here. We can very quickly move through these now that we have some idea as to what happens in the presence of these ligands. All right, I shall leave it there. This video is very long already. And I will see you in the next video. Goodbye.